Okay, so before we do example number 3, we probably should talk about how do you actually then calculate the probability of dependent events. Um, and then we'll do an example. So in the last, well, let me just say what it is. So if they are dependent, not independent, but dependent, in other words, um, one event, the probability of one event depends on the other, then the probability of A and B um, is equal to the probability of A times the probability of B given A. Now this is not an I, it's just a straight line. It's a vertical line up and down. And that symbol in mathematics means given. Okay? And so if we look at our previous example, if I wanted to know the probability of there being the first person selected and the second person being selected being a girl, then that would be equal to the probability of the first person being selected, a girl, and then multiply that by the probability of a the the first girl or the second girl, so we'll say second girl given, right? Remember that means given. The first is a girl. Okay? So then what does that mean? Well, if we look at our data, so I'm going to look at the data. The probability of the first one being a girl is 9 over 12. Okay? But that reduces down to 3 over 4. If I divide the top by 3, 9 divided by 3 is 3, 12 divided by 3 is 4. So the probability of the first one being a girl is 3 over 4 times, now this is the tricky part, the probability of a girl given that the first one is a girl. So here what I'm going to look at is I'm only going to look at the probability of the second person being a girl. So I'm going to look to see that the second person is a girl, but the first person is also a girl. So then my sample space changes because this won't count because the second person is not a girl. So then my sample space then becomes out of 9. My total possible outcomes is 9 because this is the second person's a girl, second person's a girl, second person's a girl. So I'm only going to choose this because it's a girl given that the first is a girl. Actually, I got that backwards. This is what we cross out. So we're only looking, our sample space changes because we're only looking at the first person being a girl. And so the first person is not a girl here, it's a boy, so that changes our sample space. Okay? So now my sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So my total possible outcomes then would be 9. And then I got to figure out how many of those I'm going to get a second girl based on the first one being a girl. So that would be 1, 2, 3, 4, 5, 6. Because the second person's a girl given that the first is a girl. So I'm going to look to see who has a girl first. And the second, oh wait, let me think this through. The second is a girl. No, I had it right. The second given the first is a girl. Yeah, I had it right the first time. Wait, if given that the first is a girl. No, I got to think this through. That the second is a girl. So the sample space is dependent upon it's okay to think out loud. Given that the first is a girl, Yeah, so we wouldn't count these in the sample space. I don't know. I'll have to get back to you on that one. I think it. Yeah, I think this will be the correct sample space because the first one's the girl, and we're determining the probability that the second one will be a girl. Well, in this scenario, you have to have a girl first because that's the given. So yeah, so we're getting rid of this in our sample space. That's why it's 9. Okay, I figured that out. I probably confused some of you. That's okay. Practice makes perfect. Well, anyways, it's 6 out of 9. So then when you multiply this out, you're going to get 18 over 36, which reduces down to 1/2. Now, what we've done is we've determined the probability of the first and the second person that you're choosing being a girl should be 1/2. Now, how do I determine, how can I make sure that's true? Well, we just look at our sample space, right? Out of the total sample space, out of all 12 scenarios, 1, 2, 3, 4, 5, 6 of them, half of them have 2 girls. And so that's correct. So they're dependent, and this is how we would calculate the probability. Now, I did all that because in example number 3, we have a spinner, a perfectly circular spinner that's divided into 1, 2, 3, 4, 5, 6, 7, 8 equal slices of the pie. And the question is, as part of a board game, you need a spinner which is divided into equal parts. Find the probability that you will get a 5 on your first spin, 5 on your first spin, and a number greater than 3 on your second spin. Greater than 3. Alright. So I have to determine if this is independent or dependent. Well, there's a condition, right? This is the given. We have to have a 5 first. Okay? So let that be event A. So event A is 5 on the first spin, and then event B will be greater than 3 on the second spin. So to figure out the total probability, in other words, what's the probability of this happening, I need to find the probability of A. Now, when I think about the total possible outcomes, when I spin this thing, I'm either going to get a 1, a 2, a 3, a 4, a 5, a 6, a 7, or an 8. Okay? So there's 8 possible outcomes when I spin the spinner. Now, the probability of me getting a 5 is just going to be 1, because there's only one 5 on here. Alright? So now the probability of me getting 3 or greater, again, I've got 8 possibilities. Let's count. 4 is greater than 3. 5, 6, 7, 8. So all these numbers are greater than 3. So I've got 1, 2, 3, 4, 5 favorable outcomes. Now, according to this example here, my probability of A and B occurring, because this is dependent, okay, is equal to the probability of A occurring times the probability of B occurring given that A occurred. Alright. So, are these independent or are they dependent? Wait, let me think this through. These are actually independent. While we're given that the first one is 5, because this is completely fair, we're not taking the 5 off the board. In other words, when I spin this and I click 5, I could get 5 again. So this is not conditional. This is actually independent. So then my formula needs to change. My formula needs to change to the probability of B. So if you're confused, what we're talking about is withdrawal versus replacement. So in our last scenario, with the girls, when we pulled a girl out, right? When we pulled a girl out, then what happens is we have one less girl to choose from. So that would be what we call withdrawal. Okay? Withdrawal is almost always dependent. But replacement, if I spin a 5 and I spin again, I can still spin a 5. So the first spin is completely independent of the second spin. So replacement is almost always independent. Why? Because we're technically replacing the 5. Right? We're not taking it off the board. When I spin a 5, I'm not taking the 5 off the board and eliminate the possibility of the 5 being there. And that's an important thing. So to find the probability of both these things occurring, of me getting a 5 and me getting something greater than 3, is going to be 1 over 8 times 5 over 8, which is equal to 5 over 64. If we plug that on a calculator, plug that into a calculator, we will get 0.078. And if we move the decimal 2 spaces, I get 7.8% probability of doing that. In other words, if I spin on the spinner 2 times, or 100 times, okay, 7.8 times, I'm going to get a 5 for the first number and a number greater than 3.